So it is paper ID 55, enhancing federated learning efficiency through parallel computing techniques. Uh, okay, so is there, so yes, Mr. Zia is in the meeting. I am sending you the request. Please accept as a contributor.
Hello.
Uh, yes, Engineer Zia, you are audible. Can you please share your screen and start the paper presentation?
Okay, ma'am. I will sharing my screen. Yes, ma'am. Can you see my screen?
Yes, your screen is has been shared. Please continue with paper presentation. Thank you.
Okay, ma'am. Okay. So good morning, everyone, and thank you for being here today. It's an honor to present our research at the fifth International Conference on Computational Intelligence and Internet of Things. So the title of our work is Enhancing Federated Learning Efficiency Through Parallel Computing. And my name is Ziaur Rahman, and I'm the lead author of this research. I conducted this research work in collaboration with Dr. Syed Nasir Mahmood Shah and Mr. Uzair Hassan from Institute of Space Technology, Islamabad, and Dr. Saiful Islam from WMG at University of Warwick, UK. So here are the list of contents that I will cover from introduction up to conclusion. So let's start with introduction. Federated learning is a powerful machine learning approach that protects the data privacy by allowing the multiple devices to train models without sharing the raw data. However, the optimizing FL performance requires the balancing the trade-offs like accuracy, speed, and resource use. So in this research, we evaluate the FL methods and comparing them based upon the key metrics such as accuracy and training time to find the most efficient approach. Let's move towards the related work. So the literature is basically divided into two key areas, which is federated learning and parallel computing. And for the federated learning, we have reviewed most recent six research articles. And these articles review the FL applications, categorize the methods, discuss the challenges, and the proposed optimization focused on improving the computational cost and accuracy. And for the parallel computing, we have reviewed a lot of recent research articles, and most relevant to this research is are mentioned here. And it discuss about the MPI enhances the parallel computing across the domains while utilizing the Python library MPI for to boost the Python task execution. So, for in order to find the research gap, it's an evident that there is a gap in implementing the edge device parallel computing. So, furthermore, enhancing the variety lining efficiency, particularly in computational cost and accuracy, that remains a challenge. So let's discuss about the research methodology which utilize in our experimentation. So this diagram is basically illustrates the federated learning process where multiple clients, for example, the devices or data centers or edge devices collaboratively train a global model without sharing their raw data. So the client basically shown on the right side are locally train the model on their own data and then send the updated model parameters to a central server, which is shown on the left side. So where the global model is aggregated. So this process basically preserves the data privacy while allowing the distributed learning as only model updates are exchanged between the clients and the server. And the next one is basically proposed ensemble learning MPI based model. And this proposed approach basically trains a local ML or DL algorithm. And in this case, a CNN model trains on each core with an assigned data subset. And after training, the cores communicate together and trained models on the root process. And the gather models from each core are integrated using an ensemble learning approach. And finally, the overall process or performance of the final model is assessed using a different testing datasets. And the next this diagram is basically shows how federated learning can be combined with the concept of MPI to enhance the training process by enabling the parallel processing, which can improve efficiency and accuracy. So this model specifically incorporates the convolution neural networks and some voting scheme from for ensemble learning approach. And this approach is basically or particularly beneficial in scenarios where processing large data sets quickly and efficiently is critical, such as our real-time decision-making systems or large-scale data analysis tasks. So let's discuss about the experimental setup and implementation. So this CNN model is used in our experimentation, and that experiments conducted on MNIST datasets. So this model is basically a convolutional neural network model with total of 8 layers, including 3 convolution layers, 2 max pooling layers, and 1 flattened layer. And it almost have 94,000 trainable parameters. And here is the short description about the well-known benchmark datasets. That's MNIST dataset contains almost 70,000 grayscale images of handwritten digits, and that's widely used for training and testing image recognition algorithms. And well-labeled datasets commonly used for evaluating deep learning models. So here is the experimental setup details of hardware and software. We have utilized on total 5 machines in our experimentation, and one of them are used as or utilized as a server machine, and 4 of them are used as compute node or client machines. And client 1, 2, and 3 are normal PC, and client 4 is basically supercomputer with 72 cores available. And for creating a federated learning environment, we use a socket programming from Python programming language to establish the client server environment. So let's discuss about the results. So I'm showing here the results of experiment number 1 and 2. That's for federated learning without MPI and federated learning with MPI. That's conducted on the MNIST datasets. So this slide basically demonstrates the efficiency improvement in federated learning using MPI-based parallel computing. As the number of cores increases, the training time decreases significantly while maintaining a high accuracy. So we observed the optimal performance at around 4 to 6 cores, but beyond this, the benefit stops and it declines slightly. So this shows that while MPI and parallel processing usually improve the training efficiency, the benefits stop increasing or may even decrease if you try to use more cores than the client has. So due to extra overhead or limited resources. So this can lead to inefficiencies and overhead from MPA communication as well as less effective learning due to the insufficient data per core. So this figure basically displays a comparative analysis of training times for the model on the MNIST dataset across 4 different clients, and each with a different number of cores available. The clients in the study are labeled as client 1, 2, and 3 are all with 4 cores available, and client 4 which has 72 cores available. So the x-axis represents the number of cores used, ranging from without MPI to 10 cores, and while the y-axis indicates the training time in seconds. So the client number 4 with 72 cores available significantly reduced the training time as more core utilized particularly between 2 and 6 core. The training time for client 4 drops sharply from around 63 seconds to 6 or to 5 or 4 seconds at 6 cores, and it remains low as the number of cores increases. So on the other hand, the client 1, 2, and 3 each with only have 4 cores available demonstrate a less reduction in training time, so that the times for these clients decreased modestly when the cores are added up to 4. So however, when additional cores are used beyond their available cores, the training times either slightly slightly decrease instead of increase. So, particularly for the client one and two, the increasing training time with more cores beyond the available cores can be attributed to the overhead of MPI communication and inefficiencies that arise from attempting to parallelize the task beyond the system hardware capabilities. And the next one is basically this figure displays the test accuracy of the model on the MNIST dataset for the client one, two, and three, which has 4 cores available, and the client four, which has 72 cores available. So the x-axis represents the number of cores, and the y-axis shows the test accuracy in percentage. So this figure illustrates that while MPI and using multiple cores generally enhance the training speed, but they can be negatively impact the model accuracy. MPI does not significantly affect test accuracy as long as the number of cores used matches the system's available cores. However, when the number of cores exceeds the system limits of 4 for the client 1, 2, and 3, the accuracy starts to decline more noticeably. So, suggesting that exceeding the system core's capacity introduce the complexity or inefficiencies that compromise the accuracy. So, the gradual decrease in accuracy with the increasing number of cores indicates that the parallel processing might lead to problems such as data fragmentation or inefficient synchronization, ultimately affecting the model's ability to generalize well on the MNIST dataset. So let's conclude my research work. So while the federated learning preserves the data privacy and enables the machine learning on private data, but it often underutilizes the computational resources on multi-core systems. So MPI-based parallelization reduces the training time by efficiently distributing the workload across multiple CPU cores, which making it highly effective in a high-performance computing environment. And the future work should focus on selecting the optimal number of cores for each node to further enhance varied learning scalability and performance across various domains. So here are the references, and thank you. You can ask me questions.
Thank you, Engineer Ziaur Rahman, for a very interesting presentation. So now I am going to ask the audience if they have any question. Please feel free to ask the author. Thank you.
Hello, Engineer Rahman.
Hello, sir.
Thanks a lot for your nice presentation.
Thank you,
So
sir.
I have one question. It is very basic and maybe very general.
Yeah.
You have performed your experiments on multi-core system,
Yes.
and in this case, the data might be homogeneous, right?
Yes.
So what do you think how your model or federated learning will perform on the heterogeneous data or the data from different IoT devices, and how it will impact the model's ability to converge properly?
Yeah, for currently for this research, I have only distributed the same number of samples of Amnis dataset to different clients. But it for in federated environment, yes, it could be different data types or a heterogeneous nature of the data is there. But for right now, I have divided my data samples in equal chunks and give it to each client. But I have also conducted a separate research for heterogeneous data set. And for heterogeneous data sets, it could be difficult to converge because in order to aggregate the overall data, overall models weights from different clients, we have different natures of the weights category. So yeah, it could be difficult to converge. But for the same number of samples, it is easy to aggregate it and distribute it the overall aggregated model to the clients.
Okay, thank you. So I have a few questions. Uh, First of all, you have used a benchmark data set, MNIST, and used it in federated learning with and without MPI, and you have reported the number of cores. So, what about extending the same work to the other data sets? Because the number of cores, the decision of number of cores also depends upon the quantity of the data or the size of the data or the volume of the data. And MNIST is a very small data set. So I just want to ask you that have you considered other data sets or why you have considered MNIST? Even though this is a benchmark data set and for the starting you can consider it well, but for the better understanding and the better results of this federated learning, if more data can be given, because we are using multiple cores, and on those cores we are utilizing parallel processing. So if the data set is small, so the performance may not be that efficient, because we are already receiving or already getting very good results or very good accuracy of MNIST data set. So can you highlight this point? Thank you.
Yeah, basically, we have utilized this Amnis datasets to see how our proposed model behave. Because I think in 2023 the Python library MPI is launched for programming or parallel processing to distribute data set or distribute tasks to multiple cores. So in order to validate our proposed model of parallelization using MPI, we first use this benchmark dataset, but we also conducted our research using Checkspert datasets for different disease classification. Which is a huge dataset. Yes, but for an instance, in order to validate our model, we used this initial simple benchmark dataset. But um, uh, we already have some results of large dataset also, but it could be presented in future in other research articles.
Okay, so what is so this means that the number of cores per system in the federated learning environment, they also vary, right? Or you have identified at least number of cores. For example, if there are one single server and four client machines, you have set up for your environment, and you are performing the federated learning. So now I just want to ask that how many cores on each system would be used? Have you identified it, or again it depends upon the data? And the second thing is that since you are doing federated learning, all of these machines, they are taking the same data or the parts of data. Like when we are processing the data sets, we divide usually into training and testing distribution. So have you done that, or you just have given the same data to all the machines in your environment, and you have because you mentioned about the accuracy, and there is degradation in the accuracy, right? So can you please highlight on this point as well? Thank you.
Yeah, for the selection of cores, because we have utilized total four machine as a client, and the three of them are the simple our lab PC, and we have to find out how many cores are present there, and it's a small chunk of code or that's code segment that find out how many cores are present in this in specific systems. And secondly, for the distribution of data, yes, for instance, for right now, we have given the same data set to each node, but there is another experimentation which I don't show here, which conducted on different size of dataset, but same dataset but different size to each node.
So does this affect the selection of the cores? Because the core will vary.
Yeah. It will affect because it generally it affects the positively for the training time because it reduced the model training time from like 60 second to 4 second, a huge difference. But it also affect on accuracy. But it's not noticeably. It's slightly affecting the like I can obtain test accuracy like 98%, but when I increased the number of cores, it reduced to 97%. But we can see that the training time, the reduction in training time is huge. So yeah, it affect positively for the training time, but negative for the test accuracy because it distribute the data into two small chunks. So yeah, it obviously affect the test accuracy. So we can if we increase the number of cores as the system already have. If the system have 4 cores available, you can divide the data chunks into 4 subsets. But if the system have 4 and you are dividing into 8 chunks, it definitely affect on the test accuracy.
Okay, thank you for your nice presentation. Thank you, Engineer Zia. So we are going to move now to the next presentation, which is paper ID 5, tumor detection using deep learning.